In this video, I'd like to supplement our conversation that we've been having in class this week for Calculus 2. We're learning about new methods of integration, specifically methods that use trigonometry, and we're going to learn a little bit more about trigonometric substitutions a little bit later this week. But for right now, let's see if we can integrate these two examples using trigonometric identities. Now, there is a rule in our integration list, or our table of integrals, and I believe this one's associated with number 37. You can look at that when we're done here to check our work, but let me just walk through a couple examples, or walk through a technique here and see if this helps. First thing that I'm going to do is I'm going to rewrite this integral as sine squared of x times sine of x dx. And I'm doing that because I'm trying to create this sine squared of x. If you recall, we have a trigonometric identity that states that sine squared of x plus cosine squared of x is equal to 1. So I'm going to make the claim that this sine squared of x could actually be rewritten as 1 minus cosine squared of x, and we'll multiply that by sine of x dx. Now you might be thinking to yourself, well, this just made things a whole lot worse. These two steps didn't do anything to help the work that we're doing so far, but I would actually beg to differ. This expression now looks like a product of two functions, and if we were to do so carefully, I think we can select an inner function, I'm going to call it cosine of x, such that the derivative of the inner function exists elsewhere in the expression. And so this leads me to believe that this expression, this integral, can be completed now by using u substitution. We didn't really have that available at the beginning here. The derivative of sine cubed of x didn't exist, but now the derivative of cosine does exist in the form of sine x dx, and we can make this substitution. So we can evaluate the integral of 1 minus u squared du and proceed from here. Although I shouldn't go too far because I just realized a mistake. The derivative of cosine is the opposite of sine, so we need to introduce a negative symbol inside here as well. So I'm going to include that negative sign out front. So there we go. Sine of x dx needs to be negative sine of x dx in order to replace u. So I'll put this negative sign here and move it from the other side. There we go, that's a little bit better. So now where we see sine of x dx, we can replace that with negative du. Okay, just to make things a little bit neater, I'll go ahead and distribute and remove the parentheses. So we now have the integral of, well, let's call this u squared minus 1 du. Therefore our antiderivative is going to be 1/3 u cubed minus u plus c. And when we make our back substitution, we end up with 1/3 of cosine of x cubed minus cosine of x plus c. And if we were to write it just a little bit more carefully, 1/3 cosine cubed of x minus cosine of x plus c. And if we consult this solution with number 37, on our table of integrals, I think they would be a pretty good match. Let's take a look at another one. In this case, if the 2 were gone, we'd have the integral of cosine squared. If I'm not mistaken, that's number 30 in our table of integrals. So again, you can go back and check it if you'd like. But let's see what we can do here on this one. Now the identity that we're going to use here was one that we learned towards the very end of our trigonometry class, and it allows us to rewrite cosine squared of theta. So I've moved my coefficient of 2 to the outside, and I need to recall a trig identity that utilizes cosine squared. Now I'll make this handout available to us in class, but for those of you that don't have me for class or don't see me in class this semester, you may want to pause the video and copy these down. Here's a good list of trigonometric identities that we had memorized in the past. If I scroll down, we can see the remaining ones that were also memorized. Now, the example that I'm going after is this one right here. If I isolate cosine squared, that would look like cosine 2 theta plus 1 divided by 2. So I could add 1 to both sides and divide by 2 and get cosine squared by itself. So I'm going to go with that expression here inside the integration. So when I come back, I've got 2 times the integral of cosine 2 theta plus 1 over 2 d theta. Now here again, it may not look like this is very helpful to us, but one thing that I notice is that I've taken this from a cosine with an exponent of 2, and I've rewritten it into cosine with a coefficient of 2 inside the argument. And we've learned how to find the antiderivative of cosine with an argument on the inside before, so that is going to be helpful to us. Now, a little bit of algebra that might help along the way is recognizing that both terms, this cosine 2 theta and the number 1, could be written as a fraction over 2. So I'm going to create a fraction that multiplies. So 1/2 cosine 2 theta d theta plus the integral of 1/2 d theta. I'm just splitting this apart into 2 different integrals that might be easier to work with. So now this 2 times, oops, and there should be a grouping symbol here. There we go. This 2 times, well, let me do it this way. Let's leave the 2 alone for a second. The integral of 1/2 cosine 2 theta d theta. Well, the 1/2 can be pushed to the outside of the integral, and now we just have to find the antiderivative of cosine 2 theta. Well, the antiderivative of cosine is going to be sine, and to offset this inside product, basically undoing a chain rule, would require us to multiply by 1/2 on the exterior. So therefore the derivative of 1/2 sine 2 theta comes out to be cosine 2 theta. If you went through a mini product rule here, you would see just that. So that completes this antiderivative. And for our second antiderivative, well, the antiderivative of 1/2 with respect to theta is just going to be 1/2 theta. And now if we distribute our 2 back into this pair of expressions, we end up with 1/2 sine 2 theta plus theta. We can't forget about our plus c. And of course you can go back and check our integration sheet, our table of integrals, and see if this does indeed match. Like I said, I believe it was rule number 30, but rule number 30 could have been utilized to complete this shortcut. Now, I hope this video helps. It was intended to be a short one, just to remind you that sometimes we have to get a little bit aggressive with our algebra, and sometimes that means including algebra with some trigonometric expressions to make our life just a little bit easier. If you have questions, please let me know. Otherwise, I'll see you in class. Thanks.